Hello, this is Truth Socrates, and welcome to a portrait of linear algebra. So if you've been following the series, in our last video, we talked about 2x2 and 3x3 determinants. And when we were developing the formula for 3x3 determinants, we ran into the concept of a permutation. So we were introduced to permutations in our last video, and we counted inversions that appeared in those permutations, and we used those to develop the formula for a 3x3 determinant. So in this video, we will look more into permutations, their properties, and therefore we call this video an introduction to permutation theory. So in our video for today, we will learn, of course, about permutations in general and the inversions that occur within these permutations. We will see how to find the inverse of a permutation because it happens to be both 1-to-1 and 1-to-2. We've heard those words before. We will see two key properties of permutations that we will need in order to understand the determinant formula and to compute it better. All right, so here's a general definition of what a permutation is. So a permutation of the set of integers 1, 2 through n is an ordered list consisting of these numbers, where each number from 1 to n appears exactly once. So in other words, a permutation is a rearrangement of these numbers. We will label permutations with lowercase Greek letters such as sigma or tau, and we will write them as sigma equals I1, I2 through In. We will call I sub k the kth component of sigma. So, as I was mentioning, we saw the permutations of 1 to 3 when we did the 3x3 determinant formula. So, you can label them this way. There's really no rhyme or reason to this order, except that was how we listed them in our table last time. So we have here, let's say sigma 5 is 3, 1, 2. So 3 is the first component, 1 is the second component, and 2 is the third component. Okay, so what about the next step? How about a permutation of 1 through 4? Well, we can take any one of these 6 permutations, and we already have 1, 2, and 3 there, so we can put the number 4, and that will give us a new permutation. I can put the 4 over here. So that gives us one permutation, a new permutation now, of 1 through 4. I can also choose to put the 4 after the 3 instead, or after the 1, or after the 2. So, how many was that? There are 4 ways to create a permutation of 1 through 4, starting with 3, 1, 2. And of course, you can do that with any of these 5 other permutations. So let's think about that. Each of these 6 can produce 4 permutations of 1 through 4. So the total number of permutations will be 6 times 4, or 24. What is another way to think about that? Well, we can start from scratch. Okay? So what if I will make a permutation from 1 to 4, and I will start the permutation with a 2. Okay, I had 4 choices for the first component. Okay, so next, in how many ways now can I choose to fill the second component? I've already used 2, so I can only use 1, 3, or 4. So there are now 3 ways to choose the second component. What if I put the 4 next? Okay. So next, for the third component, I can use only 1 or 3. I'm down to 2 choices. So how about I put 3 over here? Okay. And now for the last component, of course, I have no choice. I will have to put 1 as our fourth component. So, recap. I had 4 choices for the first component, and then I had 3 choices left, and then 2, and then 1. So in total, there are 4 times 3 times 2 times 1, 24. 24 ways to create a permutation from 1 to 3. Now, we can easily see, of course, that that idea generalizes to any permutation from 1 to n. You have n choices to put in the first component. But after you pick, let's say, 3, you are down to n minus 1 choices for the second component. And then so on. So you have n minus 1 until you're down to 3 choices, 2 choices, 1 choice left in the last component. You multiply that all together, we get n factorial. Okay, so hopefully you have seen that symbol. We see it in pre-calculus and definitely in calculus as well. So the number of permutations of 1 to n is exactly n factorial. So next, let us formalize the concept of an inversion in a permutation. An inversion occurs in a permutation sigma every time a component on the left is bigger than a component to its right. We will say that sigma is even if there are an even number of inversions in sigma, and sigma is odd if there are an odd number of inversions in sigma. We define the sign of sigma, denoted by sine sigma, to be positive 1 if sigma is even, and negative 1 if sigma is odd. So here is a permutation of 1, 2, 3, 4, 5, 6. So we see the numbers from 1 through 6 appearing exactly once. And let us count. Let us list down and let us count the inversions appearing in sigma. Okay, so here's what we're going to do. We're going to start with 4, the first component in sigma. And we will list down all the components to the right of 4, which are smaller than 4. So we see 2, and then 1, and then 3. Okay? So let's keep a running total. The total number of inversions so far is 3. Okay. There will be more. So who is next? 6 appears next. 6 is greater than 2, 5, 1, and 3. Okay, so yeah, 6 is the biggest number. So any number to the right of 6 will produce an inversion. So there are now 4 more inversions because of 6. Next, what about 2? Well, there's only one number smaller than 2, and 1 is to the right of 2. Okay, so we have 1 more to account. Running total. Next, we have 5. So 5 is greater than 1 as well as 3. So there are 2 more. The next number is 1. Sorry, there are no inversions produced by 1. 3 is the last number. It does not contribute. Okay, so what do we have? 7, 8, 10 inversions total. So therefore, of course, the sign of sigma is going to be positive 1. Okay, here's a very special permutation, and we denote it with the Greek letter iota. So of course, it's just like the letter I, but there is no dot for some mysterious reason that only the Greeks will know. So there are the numbers 1, 2, 3 up to n. Let's look for the inversions. There are none, of course. The numbers are in the correct order, increasing order, so there are 0 inversions. So, is 0 an even or an odd number? It's an even number. Remember the definition. An integer is even if it can be written as twice another integer. So 0 is twice 0. 0 is an integer. Okay, so therefore 0 is an even integer. Okay, so the sign of iota is positive 1. Now, we can think of a permutation as a function whose domain is 1 through n, and whose codomain is also 1 to n. So how will we think of the value of the permutation at an input number? Well, we can define sigma of k to be I sub k. In other words, the kth component of sigma. Let's make this table over here. Okay, so our input will be I, our output will be sigma of I, right? Who is sigma of 1? First component, so that should be 4. Sigma of 2, second component, so that's just 6. Okay, so basically just take these numbers and write them vertically down this column because our input is in the correct order. So we have 4, 6, 2, 5, 1, 3. Okay, so when we talked about invertible matrices and bijective transformations, bijective operators, okay, we said that a function from any set A to any set B is bijective if it is both injective and surjective. It is both 1-to-1 and on-to. What does 1-to-1 mean? There is no duplicated output value. Okay? There's only one input where the output is 6. Okay. What is the on-to property? The range of your function has to be the entire codomain. What does that mean? The numbers 1 to 6 have to appear at least once. Okay? 1, 2, 3, 4, 5, 6. All of the numbers from 1 to 6 appear in the output. And what did we say in that section? We said that if your function is both 1-to-1 and on-to, then there exists an inverse function from the codomain back to the domain so that the composition of the original function and this inverse function is the identity function on the domain. Or on the domain if you composed it in the opposite direction. But wait a minute, our domain and codomain are both 1 through 6 in this example. Okay, so what we're going to do is we're going to construct the inverse function to this function. All right, we are going to find the inverse in 2 steps. And when you do your homework, you can probably skip the first step. Okay, what do I mean by that? Well, remember that the inverse function simply goes from the codomain back to the domain by reversing the direction. So instead of 1 going to 4, the inverse will take 4 back to 1. Okay? So, yeah, I'm basically just going to copy this table, but I have the arrow going in the opposite direction. 6 goes back to 2, 2 goes back to 3, 5 goes back to 4, 1 goes back to 5, 3 goes back to 6. Okay? So if you squint really hard, you can't really tell the difference between these two tables. You just reverse the arrow. Okay, however, there is a however. However, we do like our arrows going left to right when we're talking about functions. Okay, so what does that mean? I need to read this table in the correct order. So where do I start? I look for 1. 1 goes back to 5. So that is what I put here in the top row. Where is 2? Right here in the output. 2 goes back to 3. There it is. Where does 3 go to? 6. 4 goes to 1. 5 goes to 4. And 6 goes to 2. There it is. So therefore, we can write down our inverse permutation. Sigma inverse is 5, 3, 6, 1, 4, 2. That's what we have over there. So of course, in your homework, you can do this more directly. Just look at the first table and produce this table right away. 1 came from 5, so 1 goes to 5. 6 came from 2, so 6 goes to 2. And so on. Just, you can even go from top to bottom. Okay? 4 came from 1, so you look at 4 over here, send it to 1. Eventually, all of this is going to be filled. Now, in pre-calc and calculus, we love graphing functions. So, we are going to show you how to graph a permutation. And it's going to be useful because we are going to discover an amazing property of permutations that we can see right away from the graph. So, I'm going to go to Paint. I will see there. So here we are in Paint. We're going to graph the permutation 462513. And the first step to do that is to write the numbers 1 through 6 in the correct order above each other. Okay, so in 2 rows, and put a nice gap between them. Okay, and you're going to see in a minute why you want to make that gap kind of substantial. Okay, here's how to draw this. The first component is 4. So remember that means that when the input is 1, the output is 4. So I have a line segment ready to go, and it's in red. So I'm going to draw what should be an arrow from 1 to 4. Okay, so let's just pretend there's an arrowhead there. I couldn't find an arrow feature over there. These just go left, right, up, and down. Boring. We need it to go diagonal. Next, 2 goes to 6. So we'll go 2, 6. Okay. So far, so good. But now, 3 will go to 2. So we're going to draw an arrow from 3 to 2. Okay, so notice there are now 2 points of intersection. All right. Next, 4 goes to 5. Ooh, 4 goes to 5. So there will be another intersection point. So we have 3 so far. Next, 5 will go all the way to 1. Okay. So when you're doing this on paper, or if you want to use paint, fine. Except you're going to have to make sure that when you connect 5 to 1, you're not going to hit any of these intersection points that you already created. Okay? So right now we just have to avoid that intersection point. And I think that can be easily done. 5 goes to 1. Avoid, avoid. Yeah. There you go. Okay? Because we also need to count these additional intersection points. 1, 2, 3, 4 more intersection points. So we have 2, 1, 4, that's 7 so far. Last input is 6, which will go to 3. Okay, so I think we're clear. All we have to do is avoid that intersection point. So 6 will go to 3. And there we go. We avoided that point. We have 1, 2, 3, 4, 3 more inversions. So that's a total of 7 plus 3 or 10 inversions. Where did we see 10 before. Ooh, I gave it away. 10 inversions. Whoops, I gave it away. So each of these intersection points is actually a representative of the inversion. For example, here we have an intersection point, and it happens because 4 is in the first component and 3 is in the sixth component. And 4 is bigger than 3. So that is this intersection point over here. What about this one? All you have to do is follow where they go. That inversion comes from 5 being on the fourth component. 5 is right there. And 1 is on the fifth component. There it is. 1 is to the right of 5, but 5 is greater than 1. So it's this 5 that produces the inversion with this 1. That dot is 5 is greater than 1. So we have 10 intersection points, 10 inversions. So we can ask, well, what about sigma inverse? Okay, how many inversions will sigma inverse have? After all, the inverse of a bijection is also a bijection. Okay, so it's another permutation of 1 through 6. Our inverse permutation was 5, 3, 6, 1, 4, 2. So we can go back and list all the inversions that new permutation will have, but we can see them right here. And in fact, we can read this graph so that we can also produce the inverse function. What is the inverse function? 1 becomes 5, 2 becomes 3, 3 becomes 6, and so on. So what is the inverse? 5, 3, 6, 1, 4, 2. 5, 3, 6, 1, 4, 2. That is exactly the inverse permutation that we got for this sigma. So the graph is going to be exactly the same. You just flip the picture. So how many intersection points will the graph have? It will also have 10 intersection points. So our original sigma is even. Our inverse, sigma inverse, is also going to be. All right, so we just discovered the first of 2 important properties of permutations. If sigma is a permutation of 1 through n, then sigma and sigma inverse have exactly the same number of inversions. Therefore, sigma and sigma inverse have exactly the same sign. They are either both even or they are both odd. The sign of sigma is exactly the same as the sign of sigma inverse. All right, so the second important property of permutations involves a swap. So we have seen and heard that word before. When you do a swap row operation, exchange 2 rows, we saw that has an effect on elementary matrices. We say that when you multiply an elementary matrix produced by a swap to any matrix on the right that's compatible, what you do is you also swap the 2 rows of the matrix on the right. So we're going to see that this property will also have an effect on determinants. Okay, so the theorem says, let sigma be a permutation of 1 through n, and let sigma prime be the permutation obtained from sigma by exchanging any 2 components of sigma, any 2 components that you like. Then the sign of this new permutation, sigma prime, is now the opposite, the negative of the sign of the original permutation. sigma. So this is different from our previous theorem, where the sign was exactly the same. This time, +1 becomes -1, -1 becomes +1. Okay, we are going to break down the proof into two cases. First case, the components are adjacent. They're next to each other. So I have prepared, boom, our last example where we have sigma, and we counted and listed down first the inversions. We have 3, 4, 7, 8, 9, 10 inversions. Total, the sign is positive, +1. So what we're going to do is we're going to switch any two adjacent components of this permutation, and we're going to check that the sign does switch. Okay, so we have to make a new permutation from sigma. We just have to pick any two components next to each other and switch them. So we can pick 4 and 6, or 6 and 2, or 2 and 5, or 5 and 1, or 1 and 3. Okay, any of those 5 pairs. How about we pick 2 and 5? Okay, so this is now going to be 5, and this is now going to be 2. Okay, so let's list down the inversions just like before. 4 is bigger than 2, 1, and 3. Okay, those are exactly the same inversions that we had in sigma. Okay, so why is that? Well, 2 is still to the right of 4. It switched over one step to the right. It's still to the right. How about 6? 6 is bigger than 5, 2, 1, and 3. Okay. We still have those 4 numbers, not quite in the same order, but they're all there because 2 and 5 switched. 5 was to the right of 6, still to the right of 6. 2 is to the right of 6, still to the right of 6. So nothing changed for 6. 5. The next number is 5. 5 is bigger than 2 and 1 and 3. Oh, wait a minute. 5 is down here. Uh-oh. So we have not just 1 and 3, but also 2. Okay, so let's think about that. 2 was to the left of 5. Now we switched. So 5 is to the left of 2. So we gained an inversion. Okay? What's our running total so far? We have 3 and 4 and 3. Okay, next on our list, we have 2. Any inversions? Yes, 2 is bigger than 1. Oh, 2 was bigger than 1 because 1 is to the right, and 1 is still to the right of 2. Okay, and what about 1? 1 is not bigger than anybody, and 3, the last number, never counts. Okay, so what do we have total? We have 3 and 4 and 3 and 1. So we have a total of 11 inversions. Aha. So what happened? We gained an inversion. So the sign of the new inversion, which is sigma prime, is now negative. Okay, and you might say, oh, you just got lucky there. Okay, what if you had switched, for example, 5 and 1? Okay, so yeah, why don't we make a little bonus example right here? That's our original. What if we had switched 5 and 1? Okay, so quickly, 4 is still bigger than 2, 1, and 3. Same. 6 is still bigger than 2, 1, 5, and 3. Ooh, same. 2 is bigger than 1. Oh, same. 1 is not bigger than either one. Oh, same. 5 is bigger than 3. Oh, check it out. 5 is bigger than 3 only. Okay, so this time, instead of gaining an inversion, you lost an inversion. We should be looking actually at this original one. Okay, 5 is bigger than 1 and 3. 5 is now only bigger than 3. So we lost an inversion here. There are only 9 inversions this time. So the sign of this new permutation, sigma prime, is now -1. Still negative, the opposite of the original sign. Okay, so now what happens if the components that we switch are not next to each other? They're not adjacent. So we switch, what was it, 2 and 5 earlier? So what if we now switch 6 and 1? Okay, so they're a little bit of distance from each other. So let's turn the 6 into 1 and the 1 into 6. Okay, instead of actually listing out the inversions, we're going to do something more intelligent. Okay, and here's what. We can list them out and we can see, oh, there are now, instead of 10, there are now only 5 inversions. So that's, again, odd, that's negative. That doesn't prove anything. A proof has to be general. Okay, so although we are looking at an example, okay, we're going to see that there are general principles that we can learn from that example. So, what are we going to do? I made this little table here. Don't think of it as a matrix, that's fine. But we're going to list sigma in the top row. Okay, now what do we have to do? We said in case 1 that if you swap 2 adjacent components, you are changing the sign from plus to minus or minus to plus. Okay, so what are we going to do? I want this 6 to eventually be here in the 5th component. So the clever thing is, instead of switching 6 and 1 directly, we're going to switch adjacent components, one pair at a time. So to get the 6 over here, it has to first swap with the 2. Okay, so we get 4, 2, 6, 5, 1, 3. Okay, next, 6 has to swap with the 5 to get it closer to the 5th component. 4, 2, 5, 6, 1, 3. Okay, so I mentioned general principles. Every time you do a switch or a swap, you change the sign. So the original sigma is +1, the second is -1, we're back to +1. Okay, but 6 is not yet where it's supposed to be. We have to do one more swap. 4, 2, 5, 1, 6, 3. Okay, 6 is now where it's supposed to be. Okay, what about 1? Okay, 1 has to go to the second component. So now it has to scoot over to the left. 1 has to swap with 5. 4, 2, 1, 5, 6, 3. Are we there yet? Are we there yet? No, we have one more switch to go. But where are we so far? Original was plus, minus, plus, minus, plus. Okay, so when we swap one more time, we're going to get 4, 1, 2, 5, 6, 3. Are we there yet? Are we there yet? 4, 1, 2, 5, 6, 3. So that is exactly our sigma prime. But let's think even more generally. Okay, you have any permutation that you have over here. And it doesn't even have to be from 1 to 6. It could be 1 to 6 million. Okay, but you take 2 of those components and they're not next to each other. Okay, so let's see. 6 was in the second, 1 was in the fifth. Okay? So how many swaps did we have to do? 1, 2, 3. How do you get 3 from 2 and 5, second and fifth component? 5 minus 2 is 3. Okay, so in the forward direction, the number on the left has to move I1 minus I2, whatever you want to call those two components. That's how many swaps you have to do to bring the number on the left to its correct position on the right. But now, what about the 1 that has been moved to the left? Okay, so it needed 3 swaps for the 6 to go to the correct position, but the 1 only needed 2 swaps. Okay, so we have 1, 2, 3 swaps for the 6, 5 minus 2, and then the 1 only needs 2 swaps to go to the left. Okay, so in general, if we have k swaps to the right, we will have k minus 1 swaps to the left. Okay, for a total of k plus k minus 1, 2k minus 1 swaps. Is that an even or an odd number? That's an odd number. Okay, so think about flipping a switch an odd number of times. Okay, your switch is at on. Let's say that means plus. You switch it 7 times. 1, 2, 3, 4, 5, 6, 7. Now it's off. Okay, so of course, if you flip a switch an even number of times, it's back where it started. But if you switch it an odd number of times, it's at the opposite of where it started. And that is what our theorem was. All right, and as a bonus, remember when we did the 3 by 3 determinant, we saw that 3 of the terms were positive and 3 of the terms were negative. Okay, in the next video, we're going to see a formula that will work for 4 by 4, 5 by 5 determinants, any square matrix. Okay, and we're going to see that in that formula, we can conclude that half of the terms will have a positive contribution and half will have a negative contribution. Again, it has everything to do with permutations. So, as a bonus, exactly half of the n factorial permutations of 1 through n are even and half of them are odd. So this will result in exactly half of the n factorial terms in the determinant formula to have a positive contribution and half to have a negative contribution. Now, there's an easy way to see this, and that is by just erasing the first 2 components of our permutation. Okay, so what if you stepped out of the room and when you came back, you saw like, wait a minute, there are missing numbers in here. So, if you believe the commas, first thing I can ask you is, well, how many numbers are there supposed to be in that permutation? Oh, we see 4 over here, and we're missing a number on the left here, and the number on the second component here. So there should be 6. Okay, good, you're on the right track. Who are the missing numbers? Okay, well, I see 1, 2, 3, and 5. So if there's supposed to be 6, oh, I don't see 6. So 6 is one of the missing numbers. I don't see 4 either. All right, so just by seeing that, 4 and 6 are missing. Okay, so now we still don't know who this permutation is, though. Okay, there are 2 possibilities, though. Okay, so we could have 4 and 6 over here. I'm not even sure if that's, oh yeah, I got my notes. Yeah, that is the correct sigma. But if I didn't know that, It could also have been 6 and 4. Okay, so you can do that to each permutation of 1 through 6. Okay, just erase the first two numbers. Okay, so big deal. All right, where's this going? Well, what's the difference between the first and the second one? We just switched the first two components because there are only two possibilities, either 4 and 6 or 6 and 4. Okay, but what did the theorem say? If the first permutation is plus, the second one is going to be minus. Big deal. But if the first permutation is minus, the second one is going to be plus. So it is a big deal because if this were a permutation of 1 to 100, you don't want to dig into, well, who are the inversions and how many are there? That is a waste of time. What you can conclude, though, is one of these permutations is going to be plus and the other is going to be minus. So permutations come in pairs and you can match the pairs together just like you're matching socks as they come out of the dryer. Okay? Think of 2513 as a design for a pair of socks. Okay? So who are the socks in that design? The ones that begin with 4 and 6 and the ones that begin with 6 and 4. Okay? So these are the two socks that make that one pair. One of them is even, the other is odd. Which is which, it doesn't matter. All that matters is that one of them is even, one of them is odd. So the socks come in even and odd. Alright, so that is our video for today. I hope you enjoyed it. In our next video, we are going to take what we learned about permutations and we are going to develop the formula for a general n by n determinant. So until then, as usual, this is Jude Socrates signing off. You will find me on Facebook and you will find the 4th edition on Facebook as well as at kindlehunt.com. So until our next video, I hope you enjoy the rest of the day.